0 is the best score for the on-time part.
Yeah.
Hi, everybody. Our plan today, we're going to go through section 8.3. That wraps up chapter 8. Next class, chapter 8 quiz on sections 1 and 2. Class after that, chapter 8 test. Also happens to be the IA due date.
Yikes.
I'm so sorry. After that, nothing more is due from you guys. That's between you and your parents.
Wait, so what do we do? Okay, just chill.
You try not to bother Mr. Kulik, who's going to be busy trying to grind through 15 hours of IA.
Awesome. Yes.
Right. How many of those?
It's like 45 of them. Probably about 20 minutes a pop. If things are going well.
They're what, 10 pages?
Yeah.
Takes about 20 to 30 minutes to grade one. So it's like 15 hours of grading.
Yeah, that's something they can math class.
Wait, does this grade go towards like our exam?
The IA is your actual exam grade. And if you're an IB student, it's part of your IB score for the course.
Yeah.
Everybody else, it doesn't really matter other than the exam rate.
Okay, so.
Wait, so the kids that aren't in the IB program, do they still get like a grade back if I IB for it?
Yes,
Oh, okay.
but it won't really do anything.
We just like see.
You can't get any course credit for this at any place that you
But
can
for
go.
the test we keep, right, the exam.
I don't think so. I've never heard of anybody getting any college credit for the SL, for
Yeah,
any
I
SL.
think it has to be an HO. No, I haven't seen that.
Wait, so Curtis.
All right, here we go. Continue talking about probabilities. So the first 10 slides are still going to be a rehash of things that we had done in 8.1 and 8.2, but it's been a minute, so it's probably good to go over these again. So our basic rules of probability. A probability is a number between 0 and 1. If you give me a negative number, a number greater than 1 without a percent sign after it, no partial credit awarded to you for this problem. You're giving me an insane person's answer, I give you an insane person score for it. Okay? The probability of the entire sample space needs to come out to be 1 or 100%. If you take all the probability of all possible outcomes, it better sum up to be 100%. In the case of equally likely outcomes, you can calculate a probability by just looking at the number of times that event happens divided by the total number of events. And then there's the complement rule, that is the probability of P complement is equal to 1 minus the probability of A. Or I'm sorry, probability of A complement is 1 minus the probability of A. So those are all things we had talked about before. When we talk about expected value, much in the same way we calculate expected counts for the chi-squared test, you can calculate an expected value, which is just the probability of success times the number of trials. So if you're talking about flipping a coin and you flip it 10 times, how many heads should you expect to get? 5, right? Because half the time it should be heads. What if I flip the coin 11 times? Expect to get 5.5 heads? Does it matter that 5.5 heads makes no sense? No, expected values don't need to make like literal, physical, real world sense. Okay. We talked about events being mutually exclusive or disjoint. That means that there's no overlap between the two events, i.e. their intersection is empty. If two events are mutually exclusive, then the probability of the union of those two events is just the probability of one event plus the probability of the other event. That only works, though, if they're mutually exclusive, i.e. they have no overlap between them. So let's look at a quick example. So suppose we choose a student at random and determine their gender and whether they have pierced ears. Find the probability that that student has pierced ears. What's the answer? Give it to me as a fraction. Probability we have pierced ears.
103 over 178.
Correct, 103 over 178. The total of pierced ears divided by the total number of students. Oops. How about is male and has pierced ears?
19 over 178.
Okay. Now you made one little assumption in doing that, right? No? Oh no. No, you didn't. Oops. 19 out of 178, yes. Oh. Yeah. Yeah. Oh. And? Okay. How about we have male or pierced ears? Male or pierced ears. What's the answer there? Again, give it to me as a fraction. Yeah, so 84 plus 19 plus 71 all over 178, right?
Yeah.
What did you have to be careful about there? The events male and the event pierced ears are not mutually exclusive. Right? You notice if you added up the male column and the pierced ears column, you would have gotten 193. Oops-a-daisy, because you double counted male and pierced ears, right? So just pointing that out to you. I did this. Okay, this brings up the idea of our general rule for overlapping events. So again, we mentioned this, right? The same thing here. It's the thing Miss Sager gave you when you filled out that sheet of paper for her. Okay, that's why I told you to take a picture of it and save it. All right. So if we have two events and it's unknown whether they are mutually exclusive or not, or we know them not to be. If I want to calculate the union of those two events, it's the probability of A plus the probability of B minus the intersection of probability A and B. The reason you subtract the intersection is because you're double counting those people when you count. When you counted A, you counted them once. When you counted everything in B, you counted them twice. You should only be counting one time. That's why we do the subtraction at the end. So in summary, if I want to do the union of, calculate the probability of the union of two events, if they are mutually exclusive or disjoint, or their intersection is empty, those three verbs can be used interchangeably, we can just add up the two probabilities. Got it. If we do not know if the events are mutually exclusive, or we know them not to be mutually exclusive, that they are overlapping, we use the second formula. The probability of A plus the probability of B minus the intersection of the two probabilities, or the probability of the intersections. Note that the second formula still works if the two things are disjoint, because if they're disjoint, the probability in the intersection is just 0. Okay, new concept, independent events. So two events are independent if the outcome of one event does not affect the outcome of another event. Our canonical example of independent events would be flipping a coin, right? The first coin flip has no effect on the second coin flip, right? Everybody's okay with that idea? Our canonical example of a dependent event, drawing names out of a hat. By me drawing the first name out, I've changed the number of names now in the hat. So when I draw the second name out, the probability has changed because I've removed a name from the hat. Everybody's okay with that? So if there's 19 people in class, the first person had a 1 in 19 chance. The second person has a 1 in 18 chance. Jackson, looks like you're going home early. So if two events are independent, we can calculate the probability of A and B by just doing the probability of A times the probability of B. Everybody's okay with that? So if I want to know the probability of flipping a coin twice and getting heads 2 times in a row, probability of heads the first time is 1/2 times the probability of heads the second time, which is still 1/2. So the probability of getting heads 2 times in a row would be 1/4. Everybody's okay? All right. A common way for us to hide whether we're talking about independent or dependent events is by talking about with replacement or without replacement. So without replacement is code for dependent event. With replacement is code for independent event. So if I'm drawing names out of a hat, with replacement, I take a name, I read it off, I drop it back in there. We still have the same number of names in the hat for the second draw. Probability remains unaffected, right? Okay, so again, this is just a way to code independent versus dependent event. Example, suppose we have 5 green gummy bears and 4 red gummy bears. You begin by picking out 1 green gummy bear. What is the probability that the second green gummy bear will also be green if we're doing it without replacement? So how many green gummy bears were there at the start? And how many total gummy bears were there? 9. So if I draw out a green gummy bear and we don't put it back, how many green gummy bears are left? 4. And how many total gummy bears are there? 8. So the probability of drawing that second green gummy bear would be 4 out of 8, or 1/2. If I did it with replacement, if I put the green gummy bear back in after I draw it out, the probability is still 5 out of 9. Everybody's okay? So a common mistake students make is they conflate the terms mutually exclusive and independent. Those two terms are not related to each other. You can have an event that is both mutually exclusive and independent. You can have one that's independent but not mutually exclusive. You can have one that's not independent but is mutually exclusive. You can have one that's not independent and not mutually exclusive. Like, it does not matter. The two terms are not imply one another. All of those things can happen. So here's just some examples of situations where they can occur. So flipping a coin twice, both mutually exclusive. You can't get heads and tails at the same time. And independent, because the result of that first coin flip doesn't affect the second coin flip. drawing cards or drawing from a deck of cards and considering their suit, this is mutually exclusive because you can't have a card that's both hearts and diamonds at the same time, for example. But it is dependent because removing one card changes the number of cards in the deck, so the probability is different when you pull the second card. So if you're looking at the type of card, here, this is no longer mutually exclusive because cards can be two things, right? You can have a jack and a diamond at the same time. And still, we don't have independence because removing that card, but we're replacing it. So here we do have independence because we're putting the card back for the second draw. And you guys get the idea, right? So that, again, these two things can happen or not at the same time. One doesn't really affect the other. How do you know what's happening? You have to read the question to understand what's going on. Okay? The situation is going to tell you. All right, so let's look at an example. Blood types of people can be found in one of four types: O, A, B, or AB. The distributions of random blood types for randomly chosen people in the US, China, and Russia are given below. What is the probability of type AB in the USA? So how would I figure out what that question mark is for AB USA? I'm going to stop you right there. There's no multiplication.
Just take 100 and minus, take 1 and subtract 1.
Yes, that's right. Was that the same idea you're having, Ethan? Good. So 1 minus 0.43 minus 0.41 minus 0.12. What rule are we using? We're using that the probability of the sample space has to equal 1. So if I take all of the USA blood types, that better add up to give me 1, right? And likewise, if I do the same thing in Mother Russia, I can do it the same way, right? 1 minus 0.39 minus 0.34 minus 0.09. So those are my answers. Everybody cool? Okay. Dirk lives in the USA and has blood type B. Type B can only receive types O and B. What is the probability that a randomly chosen citizen, US citizen, can donate blood to Dirk? First question you should ask yourself: are blood types mutually exclusive? Yes. You can't be both blood type O and blood type B at the same time. You're one or the other, or you're some kind of medical marvel. Biology students, is that possible? I don't know enough biology about blood type stuff. That's a thing that can happen. I'm getting no answers from you guys, so I'm going to take it you don't know either. I think it unlikely. Second question you should be asking yourself, really that's all we need to know because this is an or question, right? So independence and dependence don't matter. That's an and concern. So how would I do this since they're mutually exclusive?
Just add 4, 3 plus 1.
Yeah, so probability of O in the USA and probability of B in the USA, we just add them together since they're mutually exclusive. So 0.55. You guys feel good? Okay. Next question. What is the probability of a randomly choosing a person from the US with type O blood and a person from China with type O blood? So when I read this, I hear the word and, right? So my primary concern is going to be mutually exclusive or independence? Independence. Okay? Is choosing a person from USA going to affect the blood type of the person you choose from China? Or the probability of choosing a person from China? No, because removing the person from the USA population doesn't affect the probability in China, right? Everybody agree? Okay, so these are independent events. So it's just going to be the product of the probability of O in USA times the probability of O in China. So that would be 0.43 times 0.36. Everybody's good? So you guys see how I'm used. The first thing I'm looking at is like reading the question, trying to decide like, what am I computing? Is it an and or an or problem? And then is the situation, either mutually exclusive or independent, depending on whether it's an and or question. What is the probability of choosing 3 people, 1 from the USA, 1 from China, and 1 from Russia with all type O blood? And or. And. So what do we care about? Independence. Are these events independent? Blood types of people in different countries? Yes, because they're all coming from different countries, so removal of them from the population doesn't affect the probabilities. And in all reality, with the size of these countries, even removing 1 person from the population isn't really changing the probability much. Because you're talking about hundreds of millions or billions of people. Anyway, blah, blah, blah. So you just take the probability of O in the USA times the probability of O in China times the probability of O in Russia, and you get a shade over 6%. Yee! Pretty tough to do that. What is the probability of randomly choosing 3 people, 1 from each country, all with the same blood type? Okay, first thing I would ask myself here is how many different outcomes do we have for this event? 4. What are the 4 outcomes? Excellent. All O, all A, all B, or all AB. Everybody agree? Now we've calculated how the probability of getting all O's before, right? Oh, I guess the next thing I should be asking, you said or there, right? When you said that. So what do we care about, mutually exclusive or independent? Mutually exclusive. Are blood types mutually exclusive? Yes, you can't be both type O and type A at the same time. Okay? So I just need to calculate the probability of getting all O's plus the probability of getting all A's plus the probability of getting all B's plus the probability of getting all AB's. Now, the probability of getting all O's was an AND problem. So for that calculation, I care about the independence. We identified already that these are independent events because we're drawing from different countries. So all we do is grind this through. So there's my initial setup, right? All O's plus all A's plus all B's plus all AB's. And then to calculate all A's, we multiply the A probabilities together, and then the B probabilities together, and then the AB probabilities together, and we add all those up, and you got shade over 10%. Everybody cool? Again, really important that you're able to read these and decode what you need to do. I'm going to try to talk you through the symbols and how to read this. But to some extent, you just need practice on these things to develop some intuition. It's estimated that 17% of all computers bought from one manufacturer require 1 repair job during the first month. 7% will need repairs twice in the first month, and 4% will require 3 or more repairs in the first month. I should say the wording on this question is not to my liking. I would say that a better way of reading this is it's estimated that 17% of all computers bought from one manufacturer required exactly one repair job during the first month, and then exactly 2 repair jobs in the first month, and then exactly 3 repair jobs in the first month. Why is that important? Yeah, it guarantees that we have mutually exclusive. Very good. If not, then that 7% that got 2 repair jobs would be part of the 17% that got 1 repair job. Because if you got 1, or if you got 2 repairs, you need to have 1 first and then a second one made, right? Oh, all right. What's the probability a computer will need no repairs?
100% minus all those.
Good, so we'll do the complement rule. So I'm going to start just by defining some terminology or some symbols. So A is 1 repair, B is 2 repairs, C is 3 repairs. And those are the respective probabilities. I'm going to write that down at the top so I remember my symbols. Okay, with no repairs, we identified that these are mutually exclusive events because I inserted the word exactly in there to make it super clear. As David mentioned earlier, the sum of all the outcomes should equal 1. So we plug in the stuff that we know and do a little subtraction, we get 0.7. I'm going to write that down at the top of my paper because I'm going to use that in the future. So you see at the top where I put probability no repairs. Okay, the probability that a computer will need more than 1 repair. So how many outcomes are in more than 1 repair?
No more.
Oh, no more than 1 repair. Okay, good. How many outcomes are in no more than 1 repair? 2. 0 repairs or 1 repair. Everybody agree? Those are mutually exclusive, so we can just add those 2 probabilities. So pointing up. Everybody's okay here? Again, reading is the key. Like reading the question, understanding what it's saying and what's your given. You know, no more than 1 is less than or equal to, right? What is the probability that a computer will need some repairs? What is some repairs?
Any repairs?
Greater than or equal to 1, right? So how would we do that?
1 minus 0.72.
Sure, or
Add them all.
0.7 or 0.17 plus 0.07 plus 0.04. Either one is fine. You get the same result either way, right? Now in this case, there's not much difference adding 3 things or subtracting 2 things. Those are both about the same amount of difficulty. Now if there was like a situation where there's maybe infinitely many outcomes in one way but not the other, boy, that complement can become really handy there. Mr. Kulik, are we going to look at situations where there's infinitely many outcomes? Yup, not in this chapter, but that's coming. When we talk about like a continuous distribution, like a normal distribution. We'll also talk about discrete distributions where there's finitely many outcomes, but there could be lots of them, and they're hard to count because there's lots of overlap. Like a binomial distribution. If you bought 2 computers from the manufacturer, what's the probability that neither will require repair? Is this an and or an or question? And, right? You're buying one and another, right? So if it's an and question, what do we concern ourselves with? Independence. Is one computer needing repair going to depend if the previous computer needed repairs? Think about it rationally in a real world situation. I bought one faulty computer from the store. I go back and I buy another computer. The fact the first one is faulty, is that going to affect the faultiness of the second one? should not, right? These should be independent. You guys okay with how I reason that out? Just using some common sense. I know it's maybe not that common anymore, but. Okay, so neither need repair. So probably the first does not need repair times this, and the second does not need repair. We said they're independent, so we can just multiply those two probabilities, 0.72 times 0.72, and we're done. Notice that when it comes time to actually compute our answer, is the calculation difficult? No, typically, we're just like adding and subtracting or multiplying, and it's not much to do. What's the hard part? Setting it up, right? Making sure we're adding or subtracting or multiplying the correct numbers together, and knowing why we should be adding or subtracting or multiplying. That's the hard part, is being able to read the question and know what to do. The actual doing it is pretty easy. Go ahead. Okay. Same idea here. What if we bought two computers? What is the probability they both require repair? Good. So I wrote it as a complement rule because I didn't write down the 0.28 from before, but that's fine. Everybody's good with what we did there? It's essentially the same question, right? Just as a quick aside, why couldn't I have just, why couldn't I have just done 1 minus my previous answer for this one? Guys, if you buy two computers, what are the possible outcomes? Both need no repairs. The first one needs repairs, the second one doesn't. The first one doesn't, the second one does, or they both do, right? Did we cover all possible outcomes here with those? No, that's why we can't do 1 minus our previous answer, because we're not accounting for the possibility or the outcome of like one is broken and the other isn't. You know what I'm saying? That's why. It's not, I mean, it should be obvious, but it's hard to articulate. All right. So what if you don't have a independent event? We haven't talked about at all how to deal with this. To do that, we need something called conditional probability. So this is new. So the probability that one event happens, given that another event is already known to have happened, is called conditional probability. And the notation we use is if the first event is A and the second event is B, we write P of B, vertical line A, and you read that as the probability that B happens given that A has already happened. So usually we read that vertical bar as given that, or you could read it as under the condition that. So the way we calculate these conditional probabilities is we use the formula. The probability of A given B is the probability of A and B divided by the probability of B. Everybody's okay with that? Notice that the condition is the denominator, right? And if we flip-flopped the A and the B, we'd have the probability of B given A is equal to the probability of B and A divided by the probability of A. If I look at those two formulas, what part of the formula has the same value? The numerator is very good because the probability of A and B is equal to the probability of B and A because the intersection operation is commutative. So that's just me pointing that out, that the only part of that calculation that's changing when you flip-flop the conditions is the denominator. The numerator is still the same value. Everybody's good? Okay. Oops. Let's do some conditional probability calculations using a two-way table. So let's say the event E is the grade comes from an EPS course, that stands for Engineering and Physical Sciences, in case you couldn't figure that out. And L is the event, the grade is lower than a B. Okay? And we're asked to calculate some probabilities. Before I even start calculating these probabilities, I'm going to do something first. What would I want to do first? Yeah, I want the totals here, right? So I add up the totals. What will be the probability of L as a fraction? You're close. It doesn't say B or lower, it says lower than a B.
Same thing.
Yeah, 3656 out of 10,000. Everybody agree? Okay. All right, let's do the probability of E given L. So let's go back and look at that formula again. So that's going to be the probability of E and L divided by the probability of L. So what's the probability of E and L?
That was 3656 over 10,000 over the answer we got.
So it would be 800 over 10,000 divided by 3656 out of 10,000. Since both of them are out of 10,000, guess what I can do? Just drop the 10,000s and write it as 800 over 3656. Is everybody okay with that? Okay. If I want to do the probability of L and E, what's the only part of the calculation that's going to change? The denominator. What will the denominator change from? Instead of 3656, it should be 1600. Be the probability of E. So I need the total on E. Or EPS, I guess. Whatever. Does everybody feel okay on this from doing a two-way table? Again, not terribly difficult if you know what you're looking at, right? None of this was hard. We just filled things into a formula. But you got to really understand what you're looking at, right? So you need the practice on this. Okay. So if we're looking at an AND event, the probability of A and B, and we are unsure if the events are independent, this is my general multiplication rule. So the probability of A times the probability of B given A. So worth noting here, what if we accidentally did this for independent events? Is it still going to work? Actually, it does. It's the general rule. It should work for everything. You know why it's going to work? Because the probability of B given A is just equal to the probability of B. If A doesn't affect B, it's the same thing, right? So again, much like the general rule for A union B, where if, the events were actually mutually exclusive, I still get the same answers if I did it the mutually exclusive way. Same idea here. So far, so good? All right. And I point out here that this formula is the same as the conditional probability formula, just rearranged. Whatever. All right. Let's look at an example here. Consider flipping a coin twice, and we're asked what is the probability of getting two heads. Now, first things first. 2 heads. Is that an and or an or probability? And, right? Heads and then heads again, correct? If it's an and question, what do we care about? Independence. Is flipping a coin independent? Yes. Everybody's okay? So you don't need to worry too much about the conditional probability. We'll write it in there anyway, but since this is independent, it doesn't really matter. We'll do another example right afterwards where the events are dependent. You get a feel for kind of how the problem changes, if at all, or doesn't have to change at all. You can still do them the same way. All right, so I'm going to build a tree diagram to kind of organize my thoughts here. Now, this is a pretty simple situation. You could probably do this without having to draw the tree diagram, but the more complicated the scenario gets, or the more unfamiliar the situation, kind of that tree diagram becomes a rather helpful way of visualizing what's going on. So I have my first coin toss here. Coin toss, and I can either get heads or tails, right? The probability of getting each one is a half. So if I've gotten heads, I flip the coin again, and I have 2 possible outcomes, heads or tails. Again, the probability is of getting a heads, given that I already had heads, is still 1/2, right? Everybody agree? Or if I had the other branch, same idea. So what I care about, there are 3 possible outcomes. So the first branch is heads, heads. The second branch would be heads, tails. Third branch, tails, heads. Fourth branch, tails, tails. So the one we care about is heads, heads. So if I multiply down that branch, a half times a half is a fourth, and that's my answer, right? Let's look at an example where the events are no longer independent. In fact, this is a situation where they're strongly dependent. The Pew Internet and American Life Project finds that 93% of teenagers use the internet. And that 55% of online teens have posted a profile on a social networking site. We're asked what percent of teens are online and posted a profile. Let's draw a tree diagram to organize our information here. So the first decision is online or not, right? So that'll be my first split. And then from that, my second split will be profile or not. Everybody agree? So here's my first, where's my mouse? Where'd you go, mouse? There you are. So here's my first split, online or not. How did I find? That was a loud one. How did I find that 0.07 were not online? Good. Yeah, because the probability of the sample space should equal 1, right? Okay. And then it says, from the teens that are online, 55% of them have a social networking profile. So this is a conditional probability here, right? The probability that we have a social networking profile, given that we're online. So this branch here is 0.55. How did I know this one? Yeah, 1 minus 0.55, because the probability of the sample space here, there's 2 outcomes, has to equal 1. And then if they're not online, I said the probability they have a social networking profile is 0. Why? How did I know that? Oh yeah, if you don't have internet, you can't post a profile. So obviously one of the, profile is 0 and no profile is 1. Everybody feel good on how I filled out my tree diagram? Okay. The place that I want is the yes, yes branch, online and posted a profile. So I have my two probabilities that I wrote down. We're asking an and question. So we cared about whether these were independent or dependent events. We inherently saw that they were dependent by the way we filled out our tree diagram. Everybody's okay there? So I just multiply those two boys together and I get shade over 51%. Okie dokie, artichokes. Okay, keep on cranking. Let's look at another example. So this is a situation where maybe we don't need to or again where we can draw a tree diagram to help us organize what's going on here. In an experiment, researchers place 6 green toys and 4 red toys in a container. The child is asked to select 2 toys at random. What is the probability that the child chooses 2 red toys? Let's draw a tree diagram to start. So we're going to have 2 branches, or 2 splits, right? For our first toy choice and our second toy choice. Toy choice is a hard combination of words to say. So first choice is red or green. What's the probability that we've chosen a red toy out of 10? And a green would be 6 out of 10. Our second choice, again, could be red or green. So our 4 outcomes would be 2 red toys, a red and a green and a red, and then 2 greens. The one we care about is red, though. Everybody agree? So we acknowledge that the probabilities of the first choice was 4 out of 10 and then 6 out of 10. What's the probability of choosing a red toy for my second choice? 3 out of 9. How about a green toy? 6 out of 9. Everybody's good with how we got that? We lost 1 red toy and 1 toy total. And then for the second branch, if I took a green toy out first, the probability of a red toy would be 4 out of 9, and the green would be 5 out of 9. Okay, we care about the red branch though, so we just would do probability of red times the probability of red given red. So 4 out of 10 times 3 out of 10, 12 out of 90, or 2 out of 15, or approximately 0.133, or approximately 13.3%. All of these answers would be correct and given full marks. Fractions do not need to be reduced. You can. But if you give me a decimal answer and you round, how much should you round to? 3 sig figs. If you report a percentage, what do you also need to include? The percent symbol. If you don't write down the percent symbol, I'm going to think it's a number. And there, if you tell me the probability is 13.3, that's an insane answer. There's no credit for you. Okay? So if you're going to elect to do percentages, you best get that percentage symbol on your piece of paper. Got it? This is me warning you. Let's do another. Survey of 1,000 people was performed regarding their gender and whether they were colorblind. The results are below. Here's a two-way table. What is the probability that a person chosen at random is colorblind given that the person is female? What type of probability are we being asked to compute here? You can tell from the wording. Conditional. How did you know that? Given that. Everybody good? So that one, it's really easy to see it because it literally says given that in the problem. So the probability formula, the probability that we're colorblind, given that we're female, should be the probability of female and colorblind, 2 out of 1,000, divided by the probability that we're female, 490 out of 1,000, or just simplify down to 2 out of 490? Everybody's okay? How about what is the probability a person chosen at random is a colorblind female? What type of probability is this? It's also, or this is an and, right? Colorblind and female. But those events are dependent, so we need a conditional probability to compute that. Is everybody okay there? Okay. So, colorblind, given that we're female, is going to be 2 out of 1,000 divided by 490 out of 1,000, or just 2 out of 490, times the probability that we're female, 490 out of 1,000. So 2 out of 1,000 is what we end up with. Notice that this is the same thing you would have gotten if you just went female and colorblind. That's 2 out of 1,000. You guys see that? Okay. Will it always be that way? Yeah. You'll be able to, for a problem with an and, with given a two-way table, you can just read the and values from the table. You don't have to muck around with the conditional probabilities. I'm just trying to demonstrate to you, like, the fact that you have a two-way table makes the problem a lot simpler than if you didn't. Okay. What's the probability the person chosen at random is a colorblind individual? Now, you made one little assumption there, David, that we had mutual exclusivity here, which, again, I don't think is unfair that you assumed right away, but we should at least mention that we thought about it for a minute, that male and female mutually exclusive, colorblind and not mutually exclusive, so we're safe there. I guess this is, I guess the color blindness is the only thing we have to worry about mutually exclusive, but still, either way, both categories are mutually exclusive, so we're double safe. But again, you gotta take a moment and check that, because as soon as you go bulldozing past it, it's gonna be the one time where it mattered. That's how it works for me. All right, let's look at another setup here. So it says the probability that a regular scheduled flight departs on time is 0.83, and the probability that it arrives on time is 0.92, and the probability that it arrives and departs on time is 0.78. Find the probability that the flight arrives on time given that it has departed on time. What type of probability are we being asked to compute here? Conditional. How did you know that? Given that. All right. So we want A given D. Good. Everybody agree? So just technically speaking here, 0.78 over 0.83 is not a fraction. Fractions have whole numbers in the numerator and denominator. If you multiply both by 100, that takes care of that. If you would like to give it a fraction, or you can give it a rounded decimal. But 0.78 over 0.83 is not a correct version of an answer, not an acceptable format, because it's not a fraction. Departs on time given that it arrived on time. What type of probability? Conditional. Same formula, right? A and D divided by A. Very good. So far, fairly easy, right? Again, just have to make sure that when you read the problem, you recognize, like, what type of probability am I doing? Is it an and, is it an or, is it a conditional? That's really kind of the question you should be asking yourself. So if we're uncertain whether two things are independent from context, we can check it. So if two events are independent, the conditional probability should equal the unconditional probability. The probability of A given B should just equal the probability of A. The probability of B given A should just equal the probability of B. Or you could check if the probability of A and B is equal to the probability of A times the probability of B. Usually that second one is the easier one to check because you only have one thing to check. And to do a conditional probability, you need to know the and the A and the B. So rather than checking two things, let's just check one. But it depends a little bit on what you're given. All right. Let's check now. Are the events arriving on time and departing on time independent? Again, from the context of this question, I have no clue, right? Seems like they shouldn't be, but I don't know enough about airport scheduling to know that. So what I'm going to do is I'm going to check. So I could check the conditional probabilities. Yuck, I don't want to do that. That's the hard way. What I'd rather do is check the and statement. Is the probability of A and D equal to the probability of A times the probability of D? Well, does 0.78 equal 0.92 times 0.83? Nope! What do I conclude? They are dependent or not independent. Either way, same thing. All right. Continuing on, more examples. In a certain country, the police stop drivers on suspicion of drunk driving. When stopped, drivers are either given a breath test, a blood test, or both tests, or neither. Records show that 81% of drivers are given breath tests, 40% are given blood tests, and 25% given both. What's the probability that a driver is given a test? What do you notice right away?
They don't have
Yeah, why don't they?
because they're simply people that are 25% is in both 81%.
They're not mutually exclusive, right? In this sort of situation, what I would do is I might draw a Venn diagram to kind of help me illustrate what's going on here. Okay. So what percent goes in both? 0.25. What's left to go in blood only? 0.15. How about breath only then? 0.56. I know, carrying ones is hard. At least at 1 o'clock on an afternoon, first class, we're back anyway after break. Okay. So what's the probability the driver was given a test? Yeah, 0.96. 0.15 plus 0.25 plus 0.56. Or you could have done the general rule, which is the probability of A plus the probability of B minus the probability of A and B. Either way, you're going to get the same result. Is everybody okay?
Yeah.
Again, if you drew the Venn diagram, you don't have to do the formula. If you just want to do the formula and skip the Venn diagram, that's the way I would do it. But Some of us are like visual and like, okay, Venn diagram really helps me understand what's going on. I think it's probably a good idea for starting. What is the probability the driver is given exactly one test?
25, 6,
Good. The probability of blood only plus the probability of breath only, because those two things are mutually exclusive because of what word? Exactly. Exactly one. You're only given one test. Nobody gets a brood test or a breath test. This is me combining blood and breath. Trying to be funny. Nobody laughed. Everybody's good? Okay. What about no tests? Yeah, so we can take the 0.96 for any test from before and do 1 minus that. That's probably the way I would do it. Or if you drew the Venn diagram, you'd see that the 0.04 is what's on the outside of the circles. Either way is fine. Are the events breath test and blood test independent? I don't know. I think from the context of this problem, it's unclear. How could we check? Yeah, I do the multiplication rule. It's probably the easiest. So is the probability of breath and blood equal to the probability of breath times the probability of blood? Nope. What's that mean? Dependent or not independent. Either way. Everybody okay? Good with how we check? That's the easiest check, in my opinion. I like that check the best. All right. Geometric probability of time. Let's say you have a dartboard. The radius for the board is 40 centimeters, divided into 3 regions. You score 2 points if you hit the center, 1 point for the white middle region, and 0 points for the outside region. What is the probability of scoring a 2 in one attempt?
The area of 2 over the whole area.
Perfect, yes, the area of 2 over the whole area. What is the area formula we would need to remember to do this problem? Pi r squared is the area for a circle. So this would be pi times 10 squared divided by pi times 40 squared, or 10 over 1600. I'm sorry, 100 over 1600. 10. Like good, great Googling. Everybody's okay here? What little assumption did we make in doing this problem? That when you throw your dart, you always hit the dartboard? Who here's played darts before? You hit the dartboard every single time?
No.
Yeah. Apparently this guy does. Which again, like makes the problem enormously more difficult if there's not the dartboard. Because what's the area of not the dartboard? Infinity or something? Yeah, I just like, ugh. I don't know what that means. All right. The probability of scoring a 1. How would we calculate the probability? What's the plan?
Area of 1.
Mm-hmm.
Subtracted by the area of 2 over total.
Great. So we want the area for the white donut shape divided by the total area. To get the area for the white donut, you can take this outer boundary for 1, that circle, minus out the green circle from the inside. But that's dead on. Yup. You guys okay with that? Somebody was good at geometry. All right. Let's keep on going. Let's talk about some at least and at most questions. At least means greater than or equal to. At most means less than or equal to. In those situations where you have at least and at most, the complement rule is typically your friend. Okay? Those are problems tailor-made to do complement rules with. Now, in these situations for this chapter, are you going to be enormously punished by having it take a really long time if you decide not to do a complement rule? No. In future chapters, would that happen? Oh, yes. All right, let's read this example. Suppose that the probability of there being rain on a given day is independent of there being rain on the day before or after. Over the next 4 days, you determine the probability that it will rain on any one day to be 30%. What is the probability of it raining on day 1 and day 2? What word do you hear there? And. In and problems, what do we care about first? Independence. Do we have independence here? Yes. How do I know? It literally tells me in the problem. It says the probability of rain is independent. Pretty good? So it's just going to be the probability of rain on day 1 times the probability of rain on day 2. We don't care about days 3 and 4, so those don't even matter. So just 0.3 times 0.3 or 0.09. Easy peasy, right? Probability of it raining on day 1 or day 2. What do we got there? What word do you hear here that's important? Or. In or problems, what do we care about? Mutually exclusive. Is rain and not rain mutually exclusive? Yes, right? It either rained on a day or it didn't. It can't both rain and not rain on the same day, or else it counts as raining on the day. Right? Everybody agree? Oh. Oh. I'm dumb. I did it wrong. Right? Because it can rain on both days. That's the mutually exclusive. That's the not mutually overlapping part. It can rain on day 1 and day 2. It's both. Right? Not that it can rain and not rain on the same day. I was thinking about the wrong part of the problem. See how easy it is to make a mistake? Just from reading, you think you get going too quick and you're not thinking about it really clearly, and whoop, there it goes, right there, and you make a mistake. What's the probability of it not raining on any one day? So again, 30% it rains on a given day. What's the percent that it doesn't rain on a given day?
Like 70%.
Yeah, 70% or 0.7. That's easy, right? What's the probability of it raining at least once? How many events or how many outcomes are in this? 4, right? Once, twice, 3 times, or 4 times. How many events are there in the outcome it rained 1 time? 4. Rains on day 1, but not the other 3. Rains on day 2, but not the other 3. Rains on day 3, but not the other 3. Rains on day 4, but not the other 3. Everybody agree? How many events are there, or how many outcomes are there in the event it rains on 2 days?
still 12. Wait.
There's still 4, right? Rains on day 1 and 2, but not on 3 and 4. 1 and 3, but not 2 and 4. 1 and 4, not 2 and 3. 2 and 3, not 1 and 4. If it rains on 3 days, how many outcomes are there? 4. Doesn't rain on day 1, doesn't rain on day 2, doesn't rain on day 3, doesn't rain on day 4. Or rains on Thursday. And how many events, or how many outcomes are there in the event it rains on all 4 days? Just one. This stinks, right? We got to add up or calculate out and add up 13 things. What's going to be easier? Doing a complement. What's the complement of it raining at least once? What's the complement of greater than or equal to 1? Less than 1, which is 0 in this case, right? So the complement, you lose the or equal to, right? So if you think about like the closed circle going to the right, the complement is the other stuff over here. So it's open circle to the left. Think back to the number line, right? When you drew inequalities back in like pre-algebra. I know. That stuff really matters. All right. So to do this, let's do the complement. The probability of it raining at least once is equal to 1 minus the probability that it rains 0 times. And how many different ways can it rain 0 times? Just 1. Doesn't that sound much better than doing 13 probability calculations and having to add up all those suckers? Me too. This is me just running through the same thing. Okay. So there we go. Everybody's okay? Oh, that wasn't that. There. That was it. Another little proof line here. So we at the end of class here. Okay, blah, 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 some more examples. That was the end of the song. So again, what happens next class? Quiz. What sections is it on? 8.1 and 8.2. If you look in the OneNote, I have a list of skills that you should be able to do. I'd also look back at the in-class examples for 8.1 and 8.2 to just kind of refresh your memory on like what to practice on. What happens the class after that? Test. On? NIA. On? 8.1, 8.2, 8.3, right? If you look at the OneNote on Minor Dame, also has a description for that test. Are you good?
Yeah.
I know, you're not, but yes.
Okay.
It'll be much work.
Sounds good.
Done with the intro.